So, what we have proved so far is that if I have a positive measurable function, I have a increasing sequence of simple functions converging to that function at all points. So, now our aim would be to define integration of positive functions first, but before that we will look at some properties of a countably additive measure. So, let us recall that. So, I have the space X and the sigma algebra F. So, mu was a measure as a countably additive measure. So, recall that mu of union A j equal to 1 to infinity equal to summation mu of A j equal to 1 to infinity if A j are disjoint. Okay. So, this is the countable additive measure. Okay. If you have such a measure, there are certain properties of mu which we require. So, let me write it as a theorem. Okay. 1 mu of union A j equal to 1 to n. So, now I am only taking finite union. So, that is the sum of mu of A j equal to 1 to n if A j are disjoint, if A j are disjoint. So, even for finite disjoint union we have the same, that is not surprising because we know that for infinite it is true. If A is contained in B, then mu of A is less than or equal to mu of B. So, this is called monotonicity. So, of course, the sets A and B are all in the sigma algebra, otherwise mu of that is not defined. Remember that mu is defined in the sigma algebra F. So, the sets, whenever we write mu of A, it is assumed that the set A is in script F. If ANs are increasing, so let us say ANs are measurable sets and ANs are increasing. So, A1 is contained in A2, contained in A3, etc. Okay. So, they will converge to some set A, right, and A is the union A j equal to 1 to n, 1 to infinity. Then mu of an, so mu of ans are positive numbers, right, that will increase to mu of a. Okay. So, in other words, if an increases to a, then mu of an increases to mu of a. So, let us prove that. Okay. So, proof. Okay. So, in the first one we have A1, A2, etc., An disjoint, right, disjoint. I can take An plus 1, An plus 2, etc., all to be equal to empty set. So, I have now infinitely many, right. So, I know that they are all disjoint. So, I know that mu of A j equal to 1 to infinity is equal to sum of mu of A j equal to 1 to infinity by countable additivity property of the measure. But mu of A j is 0 if j is greater than or equal to n plus 1, because they are all empty sets. So, here in the left hand side I will have only union up to n, because n plus 1 onwards they are empty sets. So, it does not add anything to it, and here when I look at the summation j equal to 1 to n, I will have mu of A j some numbers, but then whatever remaining is 0 because of this, right, because they are empty sets. So, this is called the finite additivity. So, countable additivity implies finite additivity, that is of course true. For the second one, I have A and B such that A is contained in B. So, B is bigger, so it should have bigger measure, right, that is what we want to prove. So, let us see. So, mu of B I can write as mu of B minus A union A, right. So, let us say this is B and some set A is inside, right. So, A is contained in B. So, I am writing B as B minus A. So, this is the part B minus A and A. So, this is a disjoint union and so it will add up, right, the measure will add up. So, this is simply B mu of B minus A plus mu of A, but mu of A is something which is positive, sorry, mu of B minus A is something which is positive. So, this tells me that this is greater than or equal to mu of A. Okay. So, that is called the monotonicity property. Now, third property. So, third property is very important. This is important. So, if A n converge, so this is essentially equivalent to, we can write another property for decreasing sequences and they are equivalent to mu being countably additive. So, I will explain that after the proof of this. So, let us look at 3. Okay. So, what I have is A n increasing to A. Well, what does that mean? That means I have the sets A 1 which is smaller than A 2, smaller than A 3 and so on. Some of them may be equal and A is simply the largest one, right. So, that is simply the union of all of them, that is the limit of A limit of A. And I want to say that mu of A n converges to mu of A. So, let us draw some pictures. So, let us say this is A 1, okay, this is A 2, this is A 3, A 3 is bigger than that, A 4 is much bigger than that and so on. Okay. So, these sets are not disjoint, but I can disjointify them. How do I do that? I look at A 1, then I look at whatever is in between, then whatever is in between here, whatever is in between here and so on, right. So, I can write A which I know is A 1 union A 2 union A 3 union A 4 union etcetera. I can write this as A 1. So, that is the first one here, union whatever is in A 2 and not in A 1. So, I look at A 2 minus A 1. Okay. Then I can write union A 3. So, whatever is in A 3, but not in A 2, okay, etcetera. So, union A j plus 1 minus A j union dot. Well, what is the advantage of this? This would be a disjoint union. Okay. And so, when I look at mu of A, this would be, because this is disjoint and mu is a countably additive measure, it will add up mu of A 1 plus mu of A 2 minus A 1 plus mu of A 3 minus A 2 plus etcetera. Now, if any of them is infinite, if any, so let us make a reduction. So, if mu of A k is infinity for some k, then mu of A is greater than or equal to mu of A k, because A is the union of A j's, and so this will also imply that mu of A is infinity, and so the both sides will be same. Okay. So, we can assume that mu of A j is finite for every j. Then what is mu of A j plus 1 minus A j? Well, this would be equal to mu of A j plus 1 minus mu of A j, right. We did this earlier. So, let me remind you of that. So, we wrote mu of B equal to mu of B minus A plus mu of A. If this and this are finite, then I can take mu A to this side, So, I will get mu of B minus A to be equal to mu B minus mu A. So, that is why we have this. Now, if you plug it in, this would be mu of A equal to mu of A1 plus, well, what happens to mu of A2 minus mu A1? So, this is mu of A2 minus mu A1 plus, well, this becomes mu of A3 minus mu of A2 plus dot dot dot. So, notice that this cancels with this cancels with this, etc., etc., which is same as limit of mu A n, and that is what we wanted to prove. Okay. So, let us stop with a corollary, a similar proof. Corollary, suppose A n are decreasing to A, what does that mean? A1 is the bigger set, A2 is smaller than A1, A3 is smaller than A2 and so on, right, it is decreasing. So, what will be A? Then A equal to intersection A n, right, n equal to 1 to, that is the limit of A n. Okay. If mu of A1 is finite, so that is important, then mu of A n, the limit is actually mu of A. So, A n decreases to A, then mu of A n decreases to mu of A. So, let me write this again, mu of A n decreases to mu of A, but you need the extra condition that mu of A1 is finite, otherwise it is not true. Okay. So, let's prove this. So, it is easy to deduce it from the earlier result. So, AIs are decreasing. So, you look at A1 minus AJ. So, let us call that BJ. Okay. So, recall that AJ is decreasing to A. Okay. So, A1 minus AJ will increase to A1 minus A. Okay. So, check this is very easy. If I have a decreasing sequence of sets, if you look at complements, that will have to be increasing, right, that is all we are using. So, Bj is a collection of sets. So, remember Bj are also in the sigma algebra, right, because they A1 Aj they are all in the sigma algebra. So, Bj are also measurable sets and it increases to A1 minus A. So, by the previous theorem, we have mu of Bj increases to mu of the limit, which is A1 minus A, right. Well, what is mu of Bj? So, mu of Bj is mu of A1 minus Aj, which is equal to mu of A1 minus mu of Aj, because everything is finite, remember that. So, this is equal to mu of A1 minus mu of Aj. Remember mu of A1 is finite. So, mu of A1 is finite. So, mu of A2 is finite, mu of A3 is finite, mu of A4 is finite, etc., everything is finite. This will converge to, so, well, not converge, it actually increases to, right, by our previous result, mu of A1 minus mu of A, okay, which is same as saying. So, mu of A1 is common here and I am taking minus. So, this tells me that mu of Aj decreases to mu of A. Okay. So, these two results are equivalent to a measure being countably infinite. So, this property, yeah, this property and the corollary we have proved later is actually equivalent to being countably additive. It is the property which characterizes the countable additiveness of the measure mu. But let us look at some example. So, one example to show why the extra condition in this is necessary. So, we have this extra condition that mu of some set is finite, that is necessary. Why is that? So, let us look at a simple example 1, 2, 3 etc. So, this is the integers, positive integers, and the sigma algebra is you take the power set all subsets of x and define mu to be the counting measure, right, counting measure. So, what is the counting measure? So, this is simply number of elements in A. So, we know that it is a measure. Okay. So, let us define A n. Okay. A n is n, n plus 1, n plus 2 and so on. So, that is a set, right. So, that belongs to script f, right, because script f is all subsets. So, this is a subset of x and so it is. What is mu of A n? Mu of A n is the number of elements in A n, but that is infinity, there are infinitely many elements there. But A n's are decreasing, right. So, A1 is the whole space, A2 is 2 onwards, A3 is 3 onwards and so on. So, the limit is A, which is the intersection Aj, j equal to 1 to infinity. Well, what will be that? That is the empty set, and mu of A is 0. Okay. So, I have mu of A n to be infinite for every n and mu of A to be 0. So, this does not converge to this. Okay. So, the condition that one of the sets has finite measure is a necessary condition. So, let me stop with an exercise. Okay. So, I have x and f. Okay. So, this is a sigma algebra. Let mu be a finitely additive measure on f. What does that mean? That is, if I take A1, A2 etc. An in a finitely many disjoint, then mu of union Aj, j equal to 1 to n equal to summation mu of Aj, j equal to 1 to n. So, this is what is called finitely additive. Countably additive would mean there are infinitely many sets disjoint and then you can add up. So, I start with a finitely additive measure. Suppose mu has the following property. So, this is the property which we just proved. Whenever I have sets A n in script f such that A n increases to A. So, remember A n increases to A meaning I have A1, I have A2 bigger than A1, A3 bigger than A2 and so on, right, and A is the union of all sets. Whenever this happens, we have mu A n increases to mu of A. Okay. Then prove that mu is countably additive. So, remember we started with a finitely additive measure and we are saying this property whatever we proved earlier assuming countable additivity. Now, we can prove that the measure is countably additive assuming that it is only finitely additive, but this extra property. Okay. So, that is what I meant by this property is more or less equivalent to being a countably additive measure. Okay. So, what we have done so far is to start with measurability of functions and we have looked at some property of the measure. In the next lecture we will start with integration of positive functions, where we will use the symbol functions and then first define integral for symbol functions, which would be immediate generalization of what we do for step functions in the case of Riemann integral. And then we take we extend it to positive measurable functions and then to real valued and complex valued functions. That is what we will do. Okay.